Okay, on to EM radiation or light and spectroscopy. So energy that travels in the form of waves is EM, electromagnetic radiation. This energy travels at the speed of light, which is 300,000 kilometers per second. That's in the vacuum of space. When it travels through something, it does slow down. As the wavelength increases, the frequency decreases. So for this question, it's going, so you have a wavelength like this, and now you have a wavelength like that. This one here has a much longer wave and therefore a lower frequency and lower energy. So I'm just going to put that over here for a second. I told you guys to remember the 3 L's. Long wave equals low energy and low frequency. Okay, so if you can just remember those 3 L's, it'll help you answer all these questions right here. So the higher the frequency, the higher the energy. The longer the wavelength, the lower or less the energy. The shorter the wavelength, the higher the frequency and the higher the energy. Okay. Let's see. The colors of the rainbow are red, orange, yellow, green, blue, and violet, with red having the longest wavelength and least amount of energy. An emission spectrum is produced when elements are vaporized in the lab, producing certain wavelengths of light, which can then be compared to a dark line or absorption spectrum. So I'm going to write absorption here. Absorption. And that is called a dark line spectrum. So they're used interchangeably. Dark line meaning it has those dark lines in a continuous spectrum. It's because the wavelengths are being absorbed. This analysis can tell us what elements are present in the star, the color of the star. The color of the star can tell us about its temperature. For example, a red star is cooler than a blue star, which means it has a lower, you could put temperature in here. You could say it has lower energy. There was a few things that would actually fit in that blank. Okay. So then scrolling down here, when stars are moving away from us, their light becomes redshifted because it's a longer wavelength. Oh, because their wavelength is longer. And their frequency is lower. Okay. When they are coming toward us, they are blue shifted because they are shorter. It should be the wavelength is shorter. This change in color of the spectrum is called the Doppler effect. What is the source of energy for the sun? That is thermonuclear fusion. So a lot of times we just say fusion, but it's really thermonuclear fusion. In the process mentioned above, hydrogen is converted to helium, and loss of mass is converted directly to energy. According to Einstein's famous formula, E equals mc squared. That's a C. Okay. So then you will have to do this on the exam as well. We look at the star. So again, this right here is the absorption or dark line spectrum that a star gives off. And then these over here are your bright line or emission spectrum that elements give off. And we compare the two to see what elements are in the star. So for the first one, I have hydrogen right underneath. And you can see, well, first off, we should know that all stars contain hydrogen, and this one also contains hydrogen. And the other important thing is I didn't have to move my lines at all. So the hydrogen is right underneath, and I can see that the missing lines, so like I'm going to point right over here, that missing black line right there is that one right there. I didn't have to move it, so I know that these lines aren't shifted. And because they're not shifted, I know that this star is not moving. And I know that when I go to check my other elements, I don't need to move them, and I shouldn't move them. So the first thing I know is this star contains hydrogen. And I know that for all stars. But the reason I want to check hydrogen is to make sure if it's red shifted or blue shifted. Then I'm going to put my, oops, let me try that again. I'm going to try my helium and put it right there. And if I look, and I didn't do this perfectly, but the lines mainly match up. I think I just didn't do it perfect. Let's see, right there. So now when I put helium there, I can see that those lines match up. And so it does in fact have helium. And then I'm going to move this one out of the way, and we'll check to see if calcium is in the star. And when I do calcium, I can see that the lines don't match up perfectly. So if I kind of put that right there, I can see that the lines don't match up. So it doesn't have calcium. When I check for carbon, okay, let's see if I get that. So they should match up, and they do for the most part. It didn't do this perfectly, but so it has carbon because the lines match up. And then finally, I'm going to check sodium. And when I check sodium, I see that the lines don't match up. My two lines, my two blue lines there are not missing, and so it doesn't have sodium. So my elements present are hydrogen, helium, and carbon. So that's what it has here. Is the star above moving toward us, away from us, or not moving? It is not moving. And how do we know? Because the lines are not shifted. So there is no red shift or blue shift. Okay. So we're good there. All right. So then we come to Hubble. And so this graph that you see here is it's really Hubble's law, and it's going to show us Hubble's constant in a second. So I'm going to do a line, and I'll do a color so we can see it. So if I drew a line of best fit through here, it's going to look something like that. It is not perfect, but it's somewhere in there. And so one thing to take away from here is the data is definitely scattered along that line. So is it more up here? Is it more down here? It is uncertain. So there's a lot of uncertainty with Hubble's is constant. And so that's why it's not a set number, but it's about 75 kilometers per second per megaparsec. Okay. So where that comes from is if you took the slope of this line, you would get approximately 75 kilometers per second per megaparsec, which means that for every megaparsec away a galaxy is, it will be traveling at 75 kilometers per second. The important thing about that is it's very easy to measure the speed of a galaxy. So if we determine the velocity of a galaxy, we can come across, hit our line, drop down, and read off how far away it is. So Hubble's constant allows us to determine how far away the galaxies are. Okay. So explain what the graph above shows. So interpret the graph. So when you're asked to interpret a graph, always compare your X and your Y axis and how they are related. And so as my distance increases, so as distance increases, the recessional, meaning how fast it's moving away, so recessional velocity increases. So that's just saying the farther a galaxy is, the faster it's moving away from us. And that's Hubble's law. Hubble's constant is this slope that we found right there. So that's how they're related. Coming over here, again, this is a very important line right here. It's a very intense color. The wavelength is approximately 656 nanometers for that red hydrogen line. And because all stars contain hydrogen, every galaxy contain stars, and so every galaxy is going to contain this very intense line, and it's that line that we're going to look for when we look for galaxies and whether they're moving towards us or away from us. So we have 4 galaxies here, and when I look at the graph over here, you can kind of see all this, and then you see this peak right here. That peak right there is that red hydrogen line. Coming over to this one, and I look at over here, and I see that peak right there. That's that red hydrogen line. That's the red hydrogen line, and that's that red hydrogen line. So those are our hydrogen lines that we're going to be looking for. And then he should be next door probably. And then, so if I look at where this line is, it looks like it's about, and it's hard to read on here, but 665 nanometers. This one next to it is at about 690 nanometers. This one over here is at about 725 nanometers. And this one over here is at about 750 nanometers. I know it's hard to see on this screen, but I'm looking at my packet here, and that's where it is. Okay. So then it asks you, explain how, by comparing a galaxy's spectrum to that of spectrum of hydrogen, they can determine the speed and direction of the galaxy. So we look for the hydrogen line and see, that's an and, see if it is red or blue shifted. Meaning if it's red shifted, it is greater than 656 nanometers, because that's where it's supposed to be, is at 656 nanometers. So if it's red shifted, because red is a longer wavelength, then it will be shifted to a higher number. If it's blue shifted, it's going to be less than 656. I see that all of these are greater than 656, so they are all red shifted. They are all moving away. The more they're redshifted, the faster they're going. So the 750 nanometers for Galaxy 4, that's going the fastest. Then the 725 for Galaxy 3, the 690 for Galaxy 2, and then so it just goes 1, 2, 3, 4, but it's based on how much they're shifted. And then show you where calculate how fast each one is going. So you'll be given this formula right here, and lambda right there, lambda prime, that is what the wavelength that you're measuring is. Lambda naught is what the wavelength should be. So that number is 656. That's where it's supposed to be. And lambda prime is what you measured it to be. That's these numbers here. And then you're going to divide by lambda naught, which is, again, what it's supposed to be, which is 656. So we're looking for how much it's shifted as a percent, which would be a percent of the speed of light, and then we're going to multiply that number by 300,000. So the way it's going to look, and I'm going to come up here to do it, we have for Galaxy 1, 665 nanometers, so I'm going to do 665 minus 656, which is going to end up being 9. I'm going to divide that number by 656, and I'm going to take that times 300,000. And if I do that out, I'm going to come up with 4,116, and my answer would be in kilometers per second. Then I would just do the same thing over for Galaxy 2. I would have 690 minus 656 divided by 656, and then all of that times 300,000, and that would give me approximately 15,549 kilometers per second. If you're doing this in your calculator, make sure you hit equals after everything that you do. For example, when I do this next one, I'm going to have 725 minus 656. I should hit equals, which will give me 69. Then I divide by 656. I should hit equals, which will give me 0.105. Then I should hit times 300,000 and hit equals, and I'll get 31,555 kilometers per second. And then for the last one, I'm just going to do 750 minus 656 divided by 656 times 300,000, and that is going to give me 42,988 kilometers per second. Okay. Coming down here. Okay, if Hubble's constant is taken to be 75 kilometers per second per megaparsec, calculate the distance of a galaxy that is moving at 800 kilometers per second. Excuse me. So for this one, I'm just going to take the 800 kilometers per second and divide it by 75. And if I do 800 divided by 75, 800 divided by 75, I'm going to get 10.67. Okay, and that is going to be in megaparsecs. So that's how far away it is. For the next one, calculate the recessional speed of a galaxy that is 1,000 megaparsecs away. So for this one, that's my distance. For every one of those megaparsecs, it's moving at 75. So I'm just going to do 75 times 1,000, and I'm going to get 75,000 kilometers per second. Okay. All right, it looks like I goofed up here and did the same exact speed and distance for these other ones. But what you really should kind of look at is that the velocity is equal to Hubble's constant times distance. And so whatever distance I give you, so here I plug it into there, and then so Hubble's constant is 75. And so I just multiply whatever distance I give you times 75. And then if I'm trying to find distance, I can move this out of the way. I can rewrite this formula. So if I'm solving for distance, I'm going to have distance equals velocity divided by Hubble's constant. And so if whatever velocity I give you, so here, I would just plug it in right there and divide that number by 75. And that will give me the distance in megaparsecs. So sorry about messing up these numbers here, but hopefully that makes sense. So then I come over here and we get to the HR diagram stuff. The first thing you should always do is kind of plot your stars on an HR diagram. So I'm just going to do a simplified one here. Remember, this is cool over here, and this is hot over here. This is dim down here at the bottom, and then bright up here at the top. Remember that negative numbers are bright. So just kind of looking up here, I'm going to do this part first just to kind of get that clear. The greatest luminosity is going to be the star that is the brightest, and a -7 for my absolute magnitude, that's going to be the brightest star. So star B has the greatest luminosity. Which star appears the brightest? For that one, I'm going to look at my apparent magnitude, and once again, the negative number, so a -7 is going to be the one that appears the brightest. Okay, so I'm going to take a second here. I'm going to plot these on my HR diagram. So when I do star A, I'm going to use 15 and 3800. So 15 is a very dim star, and 3800 is a pretty darn cool star. So it's going to be down there. This will be star A. Star B, 28,000 is pretty hot, and -7 is really bright. So star B is going to be somewhere up here. Star C at 4,000 is pretty cool, and -5 is really bright. So it's going to be up here. Star D at 18,000, pretty hot, and 12 is dim. So that's going to be my white dwarf right there. And then star E at 7,000, kind of in the middle, and 4 kind of dim, but not too dim. Going to be somewhere about right there. And then so remember that our main sequence stars are right there. Our supergiants and giants would be there, and our white dwarfs would be there. So as we go to answer these questions, which star is a supergiant? It is star C because it is located up here in the supergiants. Which star is a white dwarf? It would be star D because it's down here where the white dwarfs are. Let's see. Where would star A be located on an HR diagram? So star A is down here at the bottom right. So bottom right. It's going to put BR for bottom right. Where would star C be located? Star C would be in the top right of the HR diagram. Fusing hydrogen are going to be your 3 stars that are on the main sequence. So A, B, and E. Fusing helium, that would be your supergiant. If there was a giant there, that one as well. But remember, giants and supergiants are older stars that are fusing helium, so star C. Which star isn't fusing anything? And again, it might be fusing something a little bit, but it's mostly dead. So fusion has basically stopped. Which star will go supernova relatively soon? That would be star C because it's a supergiant. It will then go supernova. Which star will live the longest? And that should be, I should have added on the main sequence. And star A, because it's a little teeny tiny red star, is the one that will live the longest. Then E, and then B is going to live the shortest because it's so big and hot, it burns really, really fast and runs out of energy very, very quickly. And then coming over, and I didn't have this on here, I guess, but if I wanted to put these in order, and so I'm going to come back here for a second, because there probably will be some questions about which one is closest and which one is farthest. And so remember, you draw an arrow to the smaller number. So I would draw my arrow down when I compare my absolute and my apparent magnitude. So a 10 is a brighter number than 15. The smaller the number, the brighter it is. So because it appears brighter than it actually is, this one's closer. And that's why I draw like down, kind of looking at like it's towards you. This one is 10 parsecs away, because remember, absolute magnitude is from 10 parsecs, apparent magnitude is from Earth. And so star B is 10 parsecs away because it appears to be the same brightness, whether you're looking from 10 parsecs or from Earth. Star C is farther away. A 3 is really dim compared to a -5. Star D is closer because an 8 is brighter than a 12. And then star E is farther away. So the star that is the closest would be between A and D. And the way I would know which of those two is closer is by comparing the two numbers. The difference here is 5. Here, the difference is only 4. So 5 is going to be closer than 4. And then I do the same thing when I'm going for which one's farther away. The difference here is 8. And the difference here is only 3. So 8 being the bigger number, meaning that it's farther away. Okay. So then we get to the new stuff that we're doing right now. And some of these words you haven't been exposed to yet. But rocks record, changes in life forms and geologic events. Okay, so then I can cross out geologic events right over here. The principle of uniformitarianism, where is that? Over here. States that physical and biological and chemical processes we observe today have also operated in the distant past. Putting things in a sequence is relative dating. And so we get rid of relative dating here. To assume that rock layers are tilted, have been moved into that position, that is going to be original horizontality. So rocks were laid down flat and then they got tilted up from some geologic process. An unconformity is when erosion strips away some rock and leaves us not knowing what happened during that time. Six, the remains we should all know is fossils. I should have crossed these out. Unconformity is here and fossils is here. Okay, scrolling down. The blank is recent life. That's the Cenozoic. So in my room, that's the yellow paper that you see towards the end. That's the most recent time. The principle of fossil succession. States that fossil organisms succeed one another in a definite and determinable manner. A half-life is the amount of time needed for one half of the nuclei in a sample to decay to form its stable daughter isotope. Using radioactive isotopes to calculate age of rocks and minerals is a procedure called radiometric dating. Radiometric dating. Carbon dating is a form of radiometric dating. Carbon dating is used to date organic material because we are all carbon-based life forms. And then great worldwide changes in life forms on Earth mark boundaries between the different eras. Okay. Coming down here, the unconformities are these squiggly lines that you see over there and over here. So X and Y, remember they were formed from erosion. In figure 12.1, putting them in order of oldest to youngest, it should go C, D, E, M. C, D, E, and then M. So C is underneath D, which is underneath E, and then M cuts through them and moved them. Why can't I tell if M and F, which one's older? So let's see where they are. So here's M, and F is right here, and they don't interact. So I don't see if one cuts across the other, and so because of that, I don't know. So they don't interact. I just can't see when they intersect one another what happens. Okay. 16, name and describe the life that existed in each of the geologic time eras. So again, in my room, the blue paper that starts is the Paleozoic, which means ancient life, and ancient life began in the oceans, so sea life. And then it transitioned to what we're all familiar with, which is the Mesozoic, which means middle life, and that was the dinosaurs. And then we are in the Cenozoic, which again, we dominate, and we are mammals. Okay. So then number 18, a radioactive isotope has a half-life of 150 years. You start with 28 grams of the isotope. How much will remain after 450 years? So for this one, I'm going to say that it went through 3 half-lives, because 450 divided by 150 is going to give me that it went through 3 half-lives. And each half-life, so then we started with 28 grams. So I'm going to say I started with 28. After 1 half-life, I had 14, and then 7, and then 3.5. So that's 1, 2, 3 half-lives. So your answer is 3.5 grams. Okay. For number 19, if you have 100 grams of radioactive isotope and you started with 400 grams 10 years ago, underline that. What is the half-life of the element? So I first, again, need to figure out how many half-lives. So it started with 400 grams. After 1 half-life, it would have 200. and then after another half-life, it would have 100. So I know it went through 2 half-lives, and those 2 half-lives are equal to 10 years. And so each half-life is going to be 5 years. Okay, so every 5 years, you cut it in half. How much longer will it be until you're down to 6.25 grams? So I would just kind of continue on from here. I'm going to run out of room, so I'm going to erase this over here real quick. Okay, I'd go from 100 to 50 to 25 to 12.5 to 6.25. And that's where I'm going to stop because it said to 6.25 grams. So it would be an additional 1, 2, 3, 4 half-lives. Again, each one of those is 5 years. So 4 more of them, 4 times 5 is going to be 20 years. So how much longer? 20 years longer. Okay. After 3 half-lives, so remember, I'm going to write this up here. If you start off, when you're talking about percent, you start with 100%. After 1 half-life, you have 50, and then 25, and then 12.5, and then 6.25, always cutting it in half. And then so after 3 half-lives, so there's 1, there's 2, there's 3, 12.5% is what you would have left after 3 half-lives. After 5, well, here's my 4th one, so then I just have to go to 3.125, and that would be what I'd have left after 5 half-lives. 1/64th of a sample would be left after. So if I have all of something, I have 1/1. After 1 half-life, I have half, and then a 4th, and then an 8th, and then a 16th, and then a 32nd, and then a 64th. So how many half-lives was that? 1, 2, 3, 4, 5, 6 half-lives. So 6. 1/8 of a sample will be left after. So 1, 2, 3 half-lives. If 15/16 is gone, and the sample is 200 years old, how old is the sample? Well, if 15/16 are gone, that means you still have 1/16. And if I come up here, 1/16 is right here, and that would be 1, 2, 3, 4 half-lives. And if 4 half-lives is equal to 200 years, 200 divided by 4 is 50 years. I'm sorry. Half-life. Oh, the half-life is 200 years. I'm sorry. I thought I was looking for the half-life. So if each half-life is 200 years and it's been through 4 of them, 4 times 200 is 800 years. Sorry about that. Okay. And then the half-life of U-238 is 4.5 billion years. I can't read this because there's something over it. So if the Earth started with 1 million kilograms of U-238, how much is left? So basically, it's been through 1 half-life because the Earth is approximately 4.5 billion years old. So I just need to take half of that number, which will be 500,000. Okay, so you have to know the age of the Earth for that one, which is about 4.5 billion years, which we should have seen in the How the Earth Was Made videos. So coming over here, we have 3 different outcrops. And so one of the things we talked about was unconformities. These things right here are just very frustrating to geologists because they have missing layers. And then so if I were looking at 3 different areas, we can see that the unconformities happened at different periods of time. So geologists can put together a more complete picture by looking at the layers and matching them up. For instance, like here is layer A. Here it starts with layer V, but I can see there's an unconformity here, meaning that there was something above that. And here I see layer A, and under it I see layer V. Here's layer V here. So if I were putting these in order of youngest to oldest, it would go A, and then V, and then C, because these all go in order, then I have an unconformity here. And then here I see C, and under it I have B. B is not in this over here, but I know that's going to be my next layer. And then it will go E, and I can just continue on down like that. We didn't cover this in class, so I'm going to skip over it, but I thought it'd be a good place to just kind of talk a bit about it right here. Okay. This we did talk about. And so in the rock layer, okay, so if C14 undergoes beta decay, so kind of coming from over here, what does it become? So remember, in beta decay, a neutron shoots out an electron, and in doing so, it becomes a proton. And it's the number of protons that determines the atomic number, which is this number at the top here. And so in beta decay, we are going to add 1 for the atomic number. The mass doesn't change. Even though an electron does have a tiny bit of mass, we don't count it when we talk about the mass of an isotope. And so the mass doesn't change, but the atomic number does. Carbon is right here. Its atomic number is 6. So if it increases by 1, it's going to become nitrogen. And the mass won't change, so it will become nitrogen 14. Potassium 40. So potassium is right over here, atomic number 19. It undergoes electron capture. In electron capture, let me do that a different color. In electron capture, we have a proton in the nucleus. An electron comes in, and the two charges cancel out, and it becomes a neutron. So in this case, the proton goes away, and so the atomic number goes down by 1. And if the atomic number goes down by 1, and I started at potassium, which is atomic number 19, I'm going to come over to argon, which is atomic number 18. And once again, the mass won't change because the electron is considered massless as far as this goes. And then I go to U238, which is going to undergo alpha decay. And so in alpha decay, remember, 2 protons and 2 neutrons are given off. And in so doing, we're going to subtract 2 from the atomic number because we're missing 2 protons. And we're going to subtract 4 from the mass because each one of these nuclear particles have mass. So if I'm at U right here, 238, it's going to go down to an atomic number, and it's going to become thorium. And its mass is going to go from 238 to 234. Okay. And then coming down here, how do unconformities form and why are they frustrating to geologists? This is a little bit out of order, but unconformities form from erosion. And they are places where we have missing information. It's gone. Okay, so the rock that contained the fossils or whatever we're trying to understand about that area is now missing. It's like tearing out pages in a history book. Why can't carbon-14, which has a half-life of 5,730 years, be used to date material that is older than 100,000 years? Because remember how it decays? Kind of, here's my decay, like it goes to nearly 0 by the time it gets out that far because it's been through so many half-lives. There's so little left, not enough left to measure. Okay, and then explain how radiometric dating, like radiocarbon dating, works in determining the ages of rocks and fossils. So using my terrible graph over here again, so if that's the decay of the radiometric isotope. If you start with 100% and it goes down to 0, if you know what percent of it is remaining, you can use mass spectroscopy to determine how much of the isotope is left. You can come across, drop down, and read off the age. So here's your percent on the y-axis. Here is your age in years on the x-axis. and you simply find your percent, come across, drop down, and read off the age. And that is it.